Alright guys, today we're going to be looking at another kinematic example. And we're going in one direction here still. We haven't got to where we have kinematics in two directions. We'll be getting to that soon. Yesterday we looked at a whole bunch of kinematic equations kind of in sequence in a multi-step problem. This is the one that kind of gets kids, so I wanted to show you an example of what happens when you are finding the time for something to travel a certain distance and the thing has an initial velocity. Okay? If it doesn't have an initial velocity here, this whole term goes to zero, and then this becomes a lot easier to solve because you don't have to use the quadratic formula. But if we have an initial velocity, like this pronghorn does, it says if the pronghorn is initially traveling at 5.2 meters per second and accelerates at 2.5 meters per second squared, how long will it take the pronghorn to cover the next 400 meters? Okay? So basically what we got going is the pronghorn's going 5.2 to start with. When the clock starts, he's going to be accelerating at 2.5 meters per second squared for the entire time at a constant rate. And we need to know how long it's going to take him to cover the next 400 meters. Okay? Does that make sense? Now, what's the record for 400 meters for humans? Anybody know? Okay. In high school, if you can run below 50 seconds, you're flying. The Olympic guys are down in, I think, the 44s. Okay, so they can roll. Okay? But pronghorn, we all know, are faster than us. So let's check this thing out. Given these kinematic variables, okay, we can choose a quadratic formula. I keep saying that. Choose a kinematic equation that looks like this. Okay? We plug in what we know: our distance, our initial velocity, and our acceleration. The unknown is time. You guys will notice that we have a t here and a t squared here, which if we rearrange this thing and set it equal to 0, that allows us to use the quadratic formula to solve this. Okay? So you guys all know this, and hopefully you have it programmed into your calculator. T equals negative b plus or minus the square root of b squared minus 4ac all over 2a. If I've rearranged my equation like this, with the t squared, the t, and the 400 there, then this is my A, that is my B, and that is my C. Now, not to be confused, this A with acceleration, that's not the same thing. Does that make sense? Okay. We plug these in, and I've done this for you here. We plug it in. We come up with a solution of 15.92 seconds, or, because we have the plus or minus, negative 20 seconds. Okay. Now, the pronghorn is probably not going to cover the next 400 meters in negative 20 seconds. So which one is the more realistic answer? Okay. This one here, right? Okay. Now, if you have the quadratic formula programmed into your calculator, it makes this easy. You plug in that for your A, that for your B, that for your C. You understand how the quadratic formula works. You come up with the answer without having to do a whole bunch of calculations. Make sense? Okay. Now, some people don't like the quadratic formula equation because it takes them some time to do. So what I've done on this one is I've shown you that you can do this multi-step. Okay? With those kinematic variables, we can solve for final velocity using v squared equals v naught squared plus 2ax. You can plug those in, and you'll come up with a velocity equals 45.0227, which ironically is kind of interesting because it's that term in the quadratic formula. Okay. And then if we use that and plug it into another kinematic equation right here, which is basically our average speed times our time, we can come up with 400, 1/2 our final velocity plus our initial velocity. We solve for t. T comes out to be the same value, 15.929. Okay. Now here's what I would say, guys. As far as kinematic equations goes, they're all the same. They're all pretty straightforward. This is the only one that makes you do, I guess, a little bit more difficult level math, but it's really not that tough. Okay. So that's Kinematics Example, finding time when we have an initial velocity.